Okay, now we are recording the session, and we are going to speak about properties. Start by studying properties of this so-called homogeneous equation, x dot equal to ax. So remember that if we have some manipulated variables, there is an extra term which is plus bu, and u is the manipulated variable, and x is the state. So if you don't have any external actions acting on your system, you don't have u. U is 0, you just have x dot equal to ax, and x starts in some initial condition. For instance, if you have a room and you have the temperature of the room, you have an initial temperature, and then when time passes, the temperature goes away, so usually it decays. Okay? If you have a population, then you have, suppose that you have foxes and rabbits, and you have an island. So your x is the number of foxes, x1, and the number of rabbits, x2. You have an initial condition, and then when time passes, foxes eat rabbits, and rabbits multiply, and x is evolving according to itself. Okay. To have control variable would be, for instance, including hunting. So a hunter comes and can hunt more or less. Okay, that's an external action to the system. So you may understand, you may believe that this part is quite important. Actually, we are going to see that it's really important because it's the matrix A that tells you whether the system is stable or unstable, or it oscillates or it does not oscillate. Okay, so it really only depends on A. Okay, now, then the details of the evolution of the state depend also on U, but the core of the business depends on A, and we are going to see that. So let's study this x dot equal to ax. And the first thing is, suppose that you have some somehow you know how to integrate this differential equation. At this moment, you don't know how to integrate it. But you have an idea that there is a function that satisfies the initial condition and satisfies the equation. So by some method, we do it. So you can start with some initial condition, in this case, x1 equal to 1, x2 equal to 1. And I wrote the differential equation in two ways. On the right, you have the matrix form, and on the left, you have two separate linear equations. Going from one to the other, is this a problem to you? So this is just multiply matrix by a vector. So first row by x1, x2, give me x2. Okay, x2. Then second row by x1, x2, minus 1.5 x1, minus 0.8 x2. Okay, you have it. Now, suppose that you simulate this. You have a function x1 starting at 1 for t equal to 0, and another function x2 starting at 1 for t equal to 0. Could be other numbers. I just placed 1, 1. So you have these functions. This horizontal variable is time. And at each time, you have x1 and x2. Maybe I should have used colors here to know which is which, but I don't know. One is x1 and the other is x2. Then at t2, you have another point for x1 and another point for x2, and so on. So at any point, you have two coordinates. Now, you can do one thing, which is eliminate time and express x1 as a function of x2. Okay? Or if you want to think in a different way, imagine that you have time outside, it's this arrow, and at each time, you have a point in the space x1, x2. You start at the initial condition here. You see my pointer?
Yes.
So you start here at 1, 1, 1, 1, and this is for t equal to 0. And when time goes on, you follow this line, which is the solution, corresponds to the solution of the differential equation. The only thing is now, what you see is x1 and x2 together, one in function of the other. And so this is nothing more than expressing one as a function of the other. This plane, x1, x2, is called the state space, state plane. You can have state spaces with all the dimensions that you want, 4, 5, okay? If you think of the currents and the tensions, of the tensions in a Pentium computer, you can describe it by a state. What is the dimension of the state? Hundreds, thousands, tens of thousands, hundreds of thousands, millions, tens of millions. What is your idea? No idea? A tiny Pentium. You know what is a Pentium? A Pentium microcomputer. You don't know. Have you never used a Pentium? Just for curiosity. You are using one at this moment. It's your processor in your computer. Okay? So it's a microchip that does everything for you, that allows us to see each other, does all the computation. So it's a small circuit with some square inches. Okay? Something like this. Very, very small. Okay? So what is your, it is an electrical circuit with resistors and capacitors. Actually, everything is made of transistors, but they managed to transform the transistors into resistors or to capacitors when they want. And the state depends on the number of capacitors, because that defines the tensions. So how many state variables for a computer processor unit? You have an idea? Should be a big number. Well, half a million. So you have, instead of having just two variables, you have 500,000 variables. And the state is evolving in a space with 500,000 axes. Okay. Another example. For instance, oil drilling platform. You know what is a oil drilling platform? In the North Sea, as plataformas de perfuração de petróleo. To get oil in the sea, you have a platform, you build a platform. I mean, not you, but someone. Okay, it's a huge structure in metal. Okay, and you have the drill, and you get the oil. Okay, and you bring this to the sea, and it makes a hole in the bottom of the ocean. Okay, so you have this structure. This structure vibrates. So you can think of the state model for it. And of course, it's not unique because you have continuous structure, but you can approximate it. You can approximate it by assuming that the mass is concentrated in some points. Okay, so any idea of what should the state model of a oil drill platform be? One example I saw, 500 states. Okay. You might think, why what the hell they would ever think of building a state model for a oil drilling platform. They use these models to study the vibrations of the platform and to find out whether something goes wrong, if there are some micro cracks before they turn into a big crack that can destroy the structure, okay? So they have a model for the normal condition, and they are measuring the state at some points, and they compare the state that they measure with the state of the normal condition simulated by a model, okay? And they decide whether everything is normal or there is a problem, and they can even locate the problem, say, I have a micro crack here at this point, okay? And go there and fix it before it propagates and becomes a huge problem. So that's one example of utility of the system. So some of these models, in some applications, you have huge, I mean, 500,000 is a huge thing for me. I never worked, even 500, I never worked with a model of order 500. I was involved in some projects, but I was never, I mean, the largest project in which I was involved, it could be, I don't know, less than 20. After approximations. Before the approximation, say 30 states, 30 states, 30 states. Okay. It was models for boilers to produce energy with steam generation, and then a turbine, and you generate electricity. Now, this is all very old-fashioned. Huh? Everybody's ending that stuff. If you go to another area in which I was much involved, solar collector fields. Okay? In solar collector fields, you have a pipe. You have a pipe. These pipes can be very long, hundreds of meters. And there is an oil. And the state is the temperature of the oil along the pipe. So if you have if you measure the temperature, if you consider the temperature every meter, if you have 1 kilometer of pipe, that's 100 states. I was working with
what kind of a collector, sorry? What kind of a collector you worked?
Thermal, solar thermal field.
And what kind of a solar collector, like a parabolic, and
it's a parabola, so it's a parabolic mirror. And maybe I can show you a picture. Maybe I can show you something. Where do I have some photographs? No, this is furnace. Okay, you have some idea here.
Yeah, I see.
Okay, so you have these parabolas and you have this pipe, and this forms a loop. This goes and returns, and you have a pipe here, and you collect the oil over there, the fluid. This is an oil. You see this big tank.
Yeah.
Okay, and so this is the. So you have a state every meter, and this is 20 meters. So we could consider a model with 20 states, but actually we were considering an approximation, so we were using models with 7, 8 states, no more than that. Okay, but if you go to my colleague Luis Miguel Silveira, who works with models of microelectronic circuits, and then you have this alpha million of when he wants to do something, approximations or modeling, right? It's alpha million. Okay, so this is to say that, okay, the concept is this, but it can be generalized and retain this. So the notion of state space. So you have X, the state lives in a state. And you start with an initial condition and you go on integrating the differential equation. And you have this, we call it an orbit. Okay? We call this curve an orbit or trajectory of the state. Okay, so we would like to know about properties of these orbits in relation to A. So one possibility is you solve the differential equations and you find the orbits, because this is actually the solution of the differential equation. But suppose that you just want to have some qualitative idea to know whether it converges to the origin. You see that this is converging to 0, 0. Or it diverges, it's unstable, or it oscillates, or it does not oscillate. So we would like to have information about this qualitative behavior just looking at matrix A. Okay, that's our objective. So let's go. Let's go. For that, I'm going to use a method known as Euler method to understand a bit of this. And to introduce another notion. So you can approximate the derivative in this way. Do you agree with this or not? What is this? Explain me this formula. So the derivative of x is blah, 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 blah. H is something small. What is this formula?
If we compute the value of the function x at time k plus 1 multiplied by h, and compare it with the value at the point k times h, it is basically the difference in the function between those time points divided by the length of the interval that we are considering.
And if instead of approximately equal, I want to place here equal, what should I do?
Put the limit of h when h tends to 0.
Yes. Okay. So by definition, the derivative is this limit when it goes to 0. Okay. That's a so-called incremental reason. Okay, so I assume that this is an equality and I plug it there. And from equating this to AX, I get this thing. Is it obvious or not? Or do we have to do some computations? Cave.
Well, actually, the last part I didn't get, so why
if you have x of k plus 1 h minus xkh divided by h equals to ax, multiply everything by h. It appears on the left and appears on the right.
Yeah. Okay, got it.
Now make this minus x jump to the other side, and you get this.
Yeah. Now
Okay?
I got it. Okay, got it.
So if you have, if you want a time kh, and you know the state x of kh, you do this computation and you get the next state.
Now I got it.
Okay?
Okay, I got it now.
José, at this moment is thinking, com quem é que eu casei a minha filha? Logo a mais nova que era a mais bonita. Não estou a conseguir ouvir, José. E a imagem está parada. Não estou a ouvir. Ouvi assim um som brusco. Não vejo imagem. Não estou a ouvir nada.
Mas eu estou aqui, estou a ouvir.
Ok, então, José, está claro este procedimento ou não? Portanto, eu começo com... Primeiro, como é que eu obtive isto lá de cima? Não é? Fiz esta aproximação da derivada e resolvi em ordem um x de k mais 1. Vale a pena ir ao quadro branco ou não? Não estou a ouvir nada. José has been taken by off me, probably, most probably. Hello? Can you, if you can hear me, you can send a chat. Okay, let's see. That's good idea. Okay, so I see. Okay, so let's go on. So I repeat this formula here. So in state space, you start with some initial condition. And so you make k equal to 0. And you pick up the state where you are, x0. So you pick up this point. And you add what? You add x is a vector, ax is a vector, and you multiply by this scale factor h. So you multiply ax. Ax tells you in which direction you go, and you go for the length h. So you go to here to xk, xh. At xh, you do the same, but now starting at xh. So you say that x2h is xh plus this vector, a of xh, times h. So at any point where you are, your trajectory will go in a direction which is pointed by a times the state where you are. Okay? Clear?
It's clear.
Okay, now what happens is that you do this for some infinitesimal value, so very small value. So you end up with something in which these directions ax are tangent to the solution, okay, to the orbit. So you move along a trajectory. At any point, you are moving in this direction, but once you move a little bit, this changes because you are in another state. At any point, the quantity ax0 is a vector that is tangent to your trajectory. Okay. Now you can even, I'm inverting the order of the slide. Go to MATLAB, and in MATLAB you can compute this so-called vector field. At any point, you compute a times that point. And this defines the vector where you go. So suppose that you start here, you go in this direction. Right, a little bit to the right and down. Okay? if you are here, left and down. So you are doing something like turning around. Okay. So we call AX a vector field. And an equation is actually defined by a vector field. A vector field is nothing more than to put a vector at each point in state space. Okay, now you can start at whatever point you want. In this case, 2 initial conditions, 2 orbits. Okay. Now imagine that you have infinite initial conditions, infinite orbits with some pattern. So here I don't have infinite, I have, I don't know, 20 or 25, I don't remember. Okay? So we call this the phase portrait. In Portuguese, retrato de fase. In English, phase portrait. The English borrowed the French word. Okay? So the phase portrait is picking up many initial conditions and see what are the solutions from those points. Okay, up to now, this is just a definition, but some notions. Okay, remember that the solution that passes by some initial condition is unique. So these orbits, they never cross. Remember that. Okay, now, what we want to do before 6:30, it must be before 6:30 because after that Benfica is playing and I want to see the game. So my challenge is to, anyway, the class ends at 6:30. Benfica plays at 7. So my challenge is to teach you how to relate the shape of the phase portrait with the eigenvalues and the eigenvectors of matrix A. Okay? So perhaps today we do this example. We do the basic theory, and then we take one or more classes to see examples. So the first thing is to recall the notion of eigenvalues and eigenvectors of a matrix. What is the eigenvalue of a matrix? Oh, eigenvalue and eigenvector. Can you explain me?
No, I don't know.
You can explain that to me in Portuguese and then I will translate, Jose. If you don't feel comfortable speaking in
No,
English,
I don't know. No, I'm saying I don't know. I'm saying I don't know.
You don't know?
I don't know.
Okay.
No.
Cave, do you know what is the eigenvalue of a matrix and the eigenvector?
Well, actually, no. Okay. I don't recall so right now.
But you could read, but it does not help too much. You don't know how to read Portuguese.
Okay.
I had a Portuguese supervisor. When I was doing my PhD, my actual supervisor was Italian from Florence. But I had a Portuguese supervisor who was a person that was and still is a big friend of mine. And he was a person a little bit out of the common. Okay.
Yeah.
So when he told me that when he was studying, he was a very bad student during the degree. And he had to study a course on the hydraulics. So he used to tell this exam of hydraulics in which they confronted him with a picture of a dam or of a turbine and so on. And they asked him, what is this? And it was written there, okay? Dam of this type or Peltier turbine or so on. So he was reading what was. So at the end, the professor of hydraulics told him, you know very well how to read 10.
Oh, 10.
Okay, so you can read it. Okay, let's go back, concentrate on this stuff. Suppose that you multiply a vector by a matrix. What does it do? In the matrix is a square matrix. So what does it do? It perhaps rotates the vector, and it stretches it or compresses it. Okay, so it's a scaling together with a rotation in general. Now, imagine that you have the origin and you have all the vectors that start from the origin and they form a sphere. Okay, imagine all the tips of your vectors of length 1 that they form a sphere. Okay? And you multiply all these vectors by a matrix. What happens is that in general, these vectors are stretched, or compressed, or rotated. But some of them are not rotated, okay? Some of the vectors remain in the same direction as they point, but they are scaled. So these vectors whose direction remains unchanged are the eigenvectors. Em português, vetores próprios. Próprio porque é característico daquela matriz, fica invariante. Okay? Eigen is something that comes from German and means self. Self. And why self? Because the vectors, the direction is unchanged. So it's something characteristic of the matrix. Okay? So of all the vectors that you have, some remain with the direction unchanged. They are not rotated, just stretched or scaled in general. The scale factor is the eigenvalue. So the eigenvectors are the ones of a matrix, are the vectors that remain and whose direction remains unchanged when you multiply by the matrix. And the scale factor is the eigenvalue. This is what is written here. So I say that lambda I is an eigenvalue of matrix A with an associated eigenvector Vi. If I apply the matrix to Vi, so I multiply Vi by the matrix A, and what do I get? I get Vi multiplied by some scalar, which is the scale factor. So the direction does not change. Was this understandable to you? And the definition is this one. So there are the eigenvalues that satisfy this one. Okay. Now let's go to the whiteboard. Let's go to the whiteboard. So stop sharing. So the definition is A Vi equals to lambda I Pi. Okay. Now let me write this in a different way. So I have Is this correct? Sorry, I'm putting too much VIs. Right?
Yeah.
No, now it's correct.
Now it's
Now,
correct?
yeah, now it's correct.
Is this correct? So A is a matrix. What about lambda I is what? The scalar.
Just scalar, yeah.
So probably you need to change something here. I put here an identity. Okay? Because this is the same as lambda I times I VI. Okay? I VI is the same as VI. So there is an identity matrix. Is this okay?
Yeah.
José Basile is not.
Yeah, I'm hearing.
Okay.
I'm hearing.
So I want to solve this equation to get the VI. Suppose that you know the lambda I. I want to solve this equation to get the VI. Now, suppose that you have some m x equal to b. And what is x?
B divided by M.
So the m is a matrix, so
Inverse of
the inverse of m times b. Okay? You multiply on the left and you get m minus 1 m, x equal to m minus 1 b. M minus 1 m gives the identity, and then you have m minus 1 b. Okay. Let's go back to here. So what is the solution? If you know this lambda I, what is the solution with respect to vi? Remember this stuff here. What is your m?
A
Yeah,
minus
so yeah, a minus lambda I.
I.
Yeah, no, so
Okay, so you invert it and you get vi equals to a minus lambda I inverse multiplies by the vector 0. Remember that this zero is a vector, so I put here. And this is equal to what?
0.
0, because you are multiplying a matrix by a vector of zeros, you get 0. You agree?
Mhm.
So there is not, the only eigenvectors I can find are 0 eigenvectors, so it's not much exciting. No? Now, let's go back to here. This is only true if what? What is the condition that you assume? Suppose that you have this thing, a x equal to b. And so you write x equals to b divided by a. Always?
When A is different from 0.
So if a different from 0. So here, what is the condition? M minus 1 must exist. So one condition for the existence of the inverse of a matrix?
The determinant of M must be different from 0.
Okay. Now, if the determinant of this matrix, if the determinant of a minus lambda I is 0, is not 0, sorry, then you can write that. And the condition F is that if this is true, then all eigenvectors are 0. Okay? Not much exciting. Not much useful. All the matrices have the same eigenvectors. Okay? Now, but now you can play with the lambda I. So what is the condition that if you want to find solutions for this equation that are non-zero, okay? If you want to find solutions for this equation that are non-zero, what is the condition? That you must impose. Now you impose conditions on the eigenvalues, on the lambda I. What is the condition that you must impose?
The determinant of A minus lambda I must be 0.
That's right. Okay. So to find non-zero Vi, you impose that determinant of I minus lambda I is equal to 0, and you get the lambda I. Okay? And this is a polynomial equation. This is a polynomial equation in lambda I. We are going to see examples in a moment. Okay? Now, you get the eigenvalues from this equation. You get the lambda I, you plug it there, and then you have non-zero solutions. Okay? And these non-zero solutions, where do they come from? Remember, this matrix becomes non-invertible. That is to say, it has rows that are linearly dependent on the other rows. If the determinant is different from 0, all the rows are independent. They are independent vectors. But if the determinant is 0, some of the rows depend on the others. And in that case, this means that you have more unknowns than equations, because some of the equations are linearly dependent on the others. They are not really new equations. Okay? So this means that you can only find Vi up to a constant. You see? So what we do, we impose this constant. For instance, in MATLAB, you have this function I that computes the eigenvalues of a matrix. And what it does is it normalizes the length of the Vi to be 1. Okay? In simple, let's say, academic exercises, you impose the first component or one of the components, usually the first, but not always, to be 1 or to be whatever you want. 5, 7, whatever, what you want. Just some number, non-zero number. And then you compute the others. Now have the extra equation that was missing. In some problems, the Vi are probabilities, so they must add to 1. So you include this extra condition that the entries, the components of the Vi must add to 1. Okay, so you can do it whatever you want. These are just 3 examples, but you can have more. Okay. So how do you compute the eigenvalues and the eigenvectors? Okay, 0 and 0, it's an eigenvalue and an eigenvector of all the matrices. Forget about it because it tells you nothing about the structure of the matrix. Now let's look for the good solutions. For the good solutions, you start by solving this so-called characteristic equation. Then you get the lambda I. Then you plug the lambda I here, and then you solve the system of equation, imposing some, say, Vi. I usually put the I here and put 1 here. The first component, say, equal to 1, or any other options. Okay. Let's do one example. Let's do an example. Do you want to ask something before we go to the example?
No.
No? So let's do the example. So the story is here, okay? So first, you have to solve this equation. And you have to know how to compute the determinant. And then you solve this other equation with these values. For each eigenvalue, you have an associated eigenvector, remember that. So you place here lambda 1, lambda 2, lambda 3, and you get solve it for v1, for v2, for v3. Okay? And let me give you another hand. If I have a matrix, if A is A, B, C, D, what is the determinant of A? I always write it as like this: A, B, C, D, and this is what?
1 divided by AD.
No, determinant. Determinant is not 1 divided by. It's not. I'm not asking the inverse. I'm asking
Oh,
the.
sorry. Yeah. So it's AD minus CB.
AD. So this one times this one minus BC. Okay? Okay? So you have to go to your linear algebra book and how to compute the eigenvalues of a matrix. Okay, 2 by 2, 3 by 3. It's paid. I mean, it's not free. I won't tell you this unless you pay me, say, 5 chocolate almonds, each one of you, if you don't mind. So let's do the example. So compute the eigenvalues and the eigenvectors of this matrix in your notebooks. Don't look at the slides. The solution is on the slides, but don't look at the slides. Do it by yourself. Even if you are not able to do it, try, and then I will give you a hand. So you have to do A minus lambda I. Let me go to the whiteboard again. This is what? Why am I writing? What is here? What shall I write here? Lambda I. Let's use just lambda, okay? We know that it is lambda I, so I just use lambda. Okay, so here is what?
Lambda I.
Yes, but it is upper corner.
Lambda.
Lambda.
Here.
0. 0.
I.
What? Which one?
Lambda.
Lambda. Okay. Lambda I is lambda times this matrix. 1, 0, 0, 1. So you multiply a scalar by a matrix by multiplying each of the elements. So you get lambda and lambda.
So the I matrix is always 1, 1, 0, 0.
For the second order, yes. In general, I is 1, 0, 0, 0, 1, 0, 0. So you have ones in the diagonal, and then a triangle of zeros, and then another triangle of zeros. Okay?
Oh, okay.
And this matrix is such that I is equal to A is equal to A. Okay?
Okay.
So, summation of these two matrices. What shall I place here? No, Maxi, don't answer. Let the others answer now. How do I subtract matrices? Is the corresponding position, the subtraction of the corresponding position. So here,
So it's 4 minus lambda.
lambda, yes.
Then is
Here,
minus 5.
minus 5,
Then is 2.
2,
And then is minus 3 times lambda.
minus lambda. Not times, minus lambda.
Oh, sorry, yes. Sorry.
Because you are,
Yeah, sorry. Sorry.
okay? Now, you have to compute the determinant of A minus lambda I. And equate this to 0.
Then it would be 4 minus lambda plus.
Just a moment. So
3.
this is minus 5, minus 3 minus lambda. And you are saying that it's 4 minus lambda?
Yes, times.
Times?
Minus 3 minus lambda. Minus
what?
minus 5 minus 5 times 2.
So plus
10 times 10
plus 10
times 10. Yes.
plus 10. Okay. So this gives you what?
Gives you minus 12. So minus.
So you can write this as lambda minus 4, 3 plus lambda. Okay, this part. So So I have lambda squared
Minus
minus
what?
lambda
Minus 2. Minus 2. No?
minus lambda and then minus 2 because it's minus 12 plus 10 minus 2.
Yeah.
And you equate this to 0. And the solution of this is what? When you have ax squared plus
It's
b
x.
x
It's
plus
lambda minus 1. It's lambda
lambda
minus 1.
is equals
Minus
to
1.
divided by 2 minus b1 plus or minus
Okay, yeah.
square root of, when you have this equation, the general solution is x equals to, you have two solutions, 2a, and here minus b plus or minus b squared minus okay. If you were living 500 years ago and you knew this formula, you would become famous. Okay, the guy who knew the formula for x equal to 3 killed another that also knew so that he could be the only one who knew it. Okay, ask someone to kill the other guy. So you could imagine, no, how to open places for promotion to professor catedrático or associado or no, by killing the opponents. Quite interesting. So in this case, we have minus b, menos b, mais ou menos raiz quadrada, b squared, 1, plus 8 square root. So this is 1 plus 3 divided by 2, or which is 4 divided by 2, which is 2, or 1 minus 3 divided by 2, which is minus 2. Am I right? No, minus 2, no. Oops.
Minus 1.
Minus 1. Minus 1, okay, so this is minus 2 divided by 2, minus 1. So you have these two eigenvalues. Okay? You have these two eigenvalues. Now, we have to now go. We have, let's write them here. So lambda 1 is 2. Lambda 2 is minus 1, if we did not mix up these things. Okay? Now, I could have well said that lambda 2 is 2 and lambda 1 is minus 1. So the order is immaterial. What we must be is consistent with the choice of the v's. Okay? Okay. Any question?
No.
No. What should we do? I will clean up this part. Don't forget the formula, the solution formula for the second order algebraic equation. Your life might depend on that.
Yes.
Okay, so now we have this, and remember that a minus lambda I v, I will put the I here and use the lower index for 1 and 2, is equal to 0. So this equation corresponds, this matrix corresponds to this one. So you have one equation and another equation. But with the choice of lambda equal to either to 2 or -1, these equations are linearly dependent. So you pass from one to the other by multiplying by a constant. So they are not really different equations. They are the same equation. So what shall I do? I shall use just this first one. So I have 4 minus lambda v. Now I put the I here. vi1 minus 5 vi2, okay? Because I'm adding here vi1 and vi2. And I'm equating this to 0, 0, so I'm just using this stuff. Okay, and equate this to 0. Now, this is equal to 0. Then I have one equation, two unknowns. So I say this is 1. This first component is 1. So I get 4 minus lambda I minus 5 vi2 equal to 0. That is to say, vi2 is 4 minus lambda I divided by 5. And for lambda 1 equal to 2, then vi2 is equal to 4 minus 2 divided by 5 equals to 2/5. So v1, actually this is v1, this is not generic. This is v1 because I'm considering lambda 1. v1 is what is 1, the first component is 1, and the second component is 2 divided by 5. For lambda 2, which is minus 1, then v2, 2 is minus 1. I use this formula here. 4 plus 1 divided by 5, which is 1. So v2 is 1, 1. Okay? I could have taken as well 5 and 2. I could here, I could multiply by a scalar. Remember that the eigenvectors are defined up to a scale factor. So I can multiply by 5 and I get 5 and 2. Could also be used. Here, instead of 1, 1, I could instead of 1, 1, I could have 5, 5 or 7, 7 or minus 3, minus 3. Okay?
Probably this is a stupid question, but why when we multiplied the matrix times v1i v2 vi2, why did we consider only the first row, the upper
because
row?
Because I only have one equation. These two equations for this choice, remember that this only happens for this choice of these lambdas. These two equations are dependent from one from the other. They are the same equation. If you pick up the second equation,
Okay.
then you get the same result. So you have one equation but two unknowns, V1 and V2. I mean, the first component and the second. Okay? So you can what I'm saying, well, I select the first component to be 1. And then I use this equation to, now I just have the second component as unknown.
Oh no. Okay.
Was it understandable?
Okay. Yeah.
Portanto, as duas equações, com esta escolha dos lambdas, as duas equações são linearmente dependentes uma da outra. Na prática, são a mesma equação.
Excuse me,
uma equação e tem duas incógnitas.
You mean if you pick the second one, which is like 2 minus 3 minus lambda,
you would get the same result.
We will get the same result. Okay.
Because you have this choice, of the lambdas. This only happens for this, because this choice ensures that the determinant of the matrix is 0. So one row is dependent from the other.
Okay.
Okay? That's the trick. This does not happen in general. I mean, if you take lambda equal to 5, okay, the equations would give you a different value. Let's see one thing.
But the question is, if we take the lambda 1 equals to 2, if we take the first row, 4 minus...
If we take what? 2, lambda 1 equal to 2, yes? And
yes.
if we take
and
the other
take
one,
the first row,
up to it's up to a scale. It would be proportional to this one. Okay, remember that we have this scale factor. Let's do with the second row. So with the second row, I will let me see, clean up this. So I only leave the result so that we can compare. And now I use the second row. In the second row, what you have? You have 2 V I 1 minus or plus minus. Let's put the minus. Minus 3 plus lambda Vi 2 equal to 0. Okay. Now I select this one equal to 1, so I take it from B. Okay. And so I get that Vi2 is equal to 2 divided by 3 plus lambda. Now, let's make lambda equal to 2. So you get 2/5. Okay? And you got the same result. Okay? So this is because the equations are let's write the equations for this value of lambda 1 to see what happens. So for lambda 1 equal to 2, you get 4 minus 2, which is
2.
2.
Yeah.
Then you have minus 5. And then here you have 2.
2.
and minus 5.
And then
So
it's minus.
you have the same equation, no? You have 2v1
Yes.
minus 5v2 equal to 0, and 2v1 minus 5v2 equal to 0. In more complicated cases, there is a scale factor between both equations. But if you multiply one equation by a scale factor, which is not 0, you get an equivalent equation. Tells you exactly. It's a collinear equation, so you don't have any point. Okay?
But okay, but the thing is, when we found that lambda had 2 possible solutions, 2 and minus 1.
That's right.
But if you put minus 1,
Minus 1 in this matrix, then it's different.
Yes, yes,
Then it's
that's right.
independent.
That's right.
Okay.
That's right.
Okay.
And you found that the eigenvalues are what? V1, 1 and 2 divided by 5, or 5 divided by 2. So 1, 2, 3, 4, 5, and 2, 1, 2. So 1 defines this direction. It's this one. And then the other is 1, 1. 1, 1, which is more or less here, or 2, 2, which is more or less here. So you have the other defines this other direction. Okay, so 1 is here, 1, 1. But what is important is the direction, and the other is 5, 2. So it's this one. You see?
Mm-hmm.
In this case, the eigenvectors are linearly independent. We are going to study matrices only with independent eigenvectors. Okay, but we will, for the moment, this was just a story about eigenvalues and eigenvectors. Later, we are going to put this together with a differential equation, and you are going to have a very nice result. So you are going to be able to express the solution in terms of the eigenvalues and the eigenvectors in a very elegant way with a physical meaning. More questions?
No, thank you for now.
Okay, so today we learned how to compute eigenvalues and eigenvectors. That's a small victory. You will learn nothing unless you start picking up some matrices and computing eigenvalues and eigenvectors. And then in MATLAB, use the command I to check your results. And do this 3 times, 3 or 4 times, okay? Just to get, you are very rusty in basic things, basic mathematics things, okay? So the solution formula for the second order polynomial, that's high school, 15-year-old boys. Multiplying matrices, 17-year-old boys, okay?
Yes.
You must get some minimum dexterity with this, and you have to do some exercises. So what my suggestion is that you write some matrices 2 by 2, okay? Do it 2 by 2 and compute the eigenvalues and the eigenvectors, and then you use the I command that I wrote here and check your result. Remember that probably the results for the eigenvectors will be different from what you find, because the normalization of the MATLAB is that the length of the vector is 1, but the proportion between the 2 components is the same. If you divide the first component by the second or vice versa, you get the same in your result or in MATLAB. Okay. The other possibility is that you divide the first component, the components of the result of MATLAB by the first component. So the first component becomes 1, And the second becomes the second divided by the first. And this should be equal to your result. Okay? So try to do a couple, 2, 3 examples, it's enough.
Okay.
So I will stop now recording.